Okay then, so today I want to talk about the imaginary circle, otherwise known as the circle with an imaginary radius. So this is a completely legitimate form in planar geometry, provided we allow complex points. And so what we want to do is to get a kind of feel for what this object is and how we can manipulate it geometrically. So, as I've described in previous lectures, it is possible to manipulate complex points and complex lines using ordinary planar geometry without having to rely upon algebra. This is possible by the kind of method developed by von Staudt of representing such complex elements by involutions in geometry. And so we're going to use some of those ideas, but in order to introduce the idea of an imaginary circle, I'll begin by talking about the approach using Cartesian coordinates, which is a completely consistent approach. I mean, results here match up with the results you get via the sort of geometric approach I shall advocate later. The difference is that perhaps it's easier to do it with Cartesian coordinates, although maybe not quite as enlightening, since one's just working algebraically and not seeing the things in quite the same way. But anyway, let's begin by thinking about how we represent an ordinary real circle centered upon the origin. So if such a circle has a radius of r, then it's normal to think of it as being described by the equation x squared plus y squared equals r squared. So if we just limit our view to real numbers and think of the ordinary idea of a circle, then this formula describes a point which is x units across and y units up from the origin, and it gives the condition for a point to be on this circle of radius r, or another way to say it is it gives the condition for a point to be a distance r from the origin. So in this real case, this formula is justified by Pythagoras' theorem. However, it turns out that basically this same kind of formula can be thought of as describing a much richer object if we don't limit our kind of ideas to only real numbers. So if we allow x and y to be complex numbers, then we get a sort of wider view of things. So let's look at an example. If we set the radius of our circle to be 1, then this unit circle centered upon the origin is described by the equation x squared plus y squared is 1. Now, let's say that we know that the x coordinate is 1. Well, solving this equation for y, we find that y must be 0. And so this gives us a point on the circle, but we can go further. So let's suppose we then have the same kind of setup, but instead we have that x is equal to 2. So you might say, well, there's no point which has an x coordinate of 2, which lies upon this unit circle. And if you're limiting your view to real numbers, then indeed that would be true. However, if you're allowing complex numbers, then you can find such a point. So if x is 2 and y is the square root of -3, which is a imaginary number, well then that's going to also be a point of this circle. So another way we could write this value of y would be y equals I times the square root of 3, where I is the square root of -1. So this is a point upon our unit circle, since 2 squared plus the square root of minus 3 squared is going to be 4 minus 3, which is 1. So it satisfies the equation, but it's a complex point. And so what we see for a start is that even a circle with a real radius, when viewed as being part of this kind of richer system of complex points, is a much more interesting form which has all this sort of complex structure about it. And it's quite remarkable, I think, to really sort of try and realise what an interesting form this is. I mean, when x and y can be complex numbers, they're each essentially sort of two-dimensional quantities because they can have a real part and an imaginary part of variable sizes. And so what we really have is that in this wider view, our system of numbers is really a kind of four-dimensional thing, and the circle is really a sort of a two-dimensional object rather than a one-dimensional kind of closed curve as we usually think of it. Anyway, this is the real circle, and then for an imaginary circle we basically take the same idea, but rather than supposing that our radius is a number r, we suppose that the radius is a number I times r for a real number r. So in other words, the value of the radius is a purely imaginary term. And when we do that, we find that the imaginary circle, which I shall talk about using purple text, just to sort of underline the difference in the kind of object, it will be given by an imaginary circle centred upon the origin will be given by an equation x squared plus y squared equals minus r squared, because it has a radius of I times r. And so where r is a real number. And so now we have a sort of different setup, and we can ask, are there any real points on this circle? And the answer is no. There are no two real numbers that if you square them and add them together, you get a negative number. So all the points on this circle with an imaginary radius are complex points. For example, we can consider the sort of unit imaginary circle given by the equation x squared plus y squared equals minus 1. This particular circle is extremely important, and one could even make a case, I think, to say that a sort of imaginary circle is at least as important as a real circle in the way that it interacts with geometric forms. Of course, there's no real meter stick for importance in geometry, and certainly real circles play a much greater role in most people's idea of what geometry is. But these things do play some really fundamental roles, and it's very lovely to see how they fit in with geometry as a whole. Anyway, this equation x squared plus y squared equals minus 1. Let's find a point satisfying this equation. So what about if x equals 0? Well then, if y is equal to I, the square root of minus 1, that's going to be a point on our imaginary circle centred upon the origin. Okay, so now we're going to build up to a sort of purely geometric view of an imaginary circle. So let's begin by thinking about a real circle. And we'll begin by constructing a real circle using a sort of pretty standard method of construction, which is involving perpendicular lines from diametrically opposite points. So suppose these dark blue points are lying upon a sort of line that goes straight through the middle of our circle. In that case, if we have any point on the circumference of the circle and we draw a line from that point to each of these dark blue points, then those two lines that we've drawn are going to meet each other at right angles, and this is a sort of defining feature of the circle. So we can use this to construct a circle sort of conversely. So if we just draw a kind of arbitrary line out from this left hand blue point, now I'm drawing my line, maybe I'll make it red just to be a bit different. I'm drawing my red line through this light blue point, but actually this light blue point and the line it's running on have nothing fundamental to do with this construction. It's just, if you're going to have a variable line, then a good way to do it in this graphics program is to use a variable point. But essentially all that matters is I'm drawing kind of arbitrary line through this left hand dark blue point. And now to finish the construction, we draw a line that's perpendicular to this red line through this right hand blue point. Now the place where these two perpendicular lines meet is going to be a place upon our circle. So what I can do now is turn the sort of trace on of the intersection of these two lines and vary the lines. And you see as we vary the lines, a circle is swept out. So what we're going to do later is to use this same kind of construction method to make an imaginary circle. But before we do that, we're going to have a closer look at the ordinary circle and how we can understand it in a sort of more complete way. Okay then, so we're going to have a look for a start at the sort of at a geometric view of the ordinary circle, and we're going to think about it in terms of polarities. So you might want to watch my video Polarities at the Foundations of Geometry for a sort of discussion about how these special mappings called polarities are sort of fundamental things which can be thought of as in a way lying beneath conics like circles, and really we should think of things like circles as coming from polarities instead of vice versa. And that video is quite sort of based on analytic geometry, and so you may also want to check out my other video. And my other video is called The Projective Nature of Circles and Imaginary Lines. That takes a more kind of synthetic or geometric viewpoint to this issue as I'm looking at here. But the important thing really is that an ordinary circle is associated with this kind of polarity, which is a mapping that swaps around points and lines. So to work out the kind of image of a point, well, the image of a point under a polarity is called its polar, and that's a line. And if the point is external to the circle, we can find its polar just by joining that point to the circle via tangents. And the place where those tangents meet the circle is this sort of line called the polar of the point. But a polarity doesn't just map points to lines, it actually swaps around points and lines. So this blue line is mapped to this blue point, and conversely we refer to this blue point as the pole of this blue line. And this mapping is defined for all points and all lines. There's an inbuilt function to work out the polar of a point with respect to a conic, and you see it also works for points interior to the conic, interior to the circle in this particular setup. I'll just show you very briefly how you can work out the polar of a generic point such as this one interior. Just draw any two lines through the point that meet this conic. They're going to meet the conic at 4 points. And then if one just sort of draws all the possible lines between these 4 points that have been chosen, then one finds that drawing in all those possible 6 lines between those 4 points, well, 2 pairs of those lines are going to meet at new points, as you can see here and here, and joining them gives the polar of the point we're interested in. So this is the kind of quadrangle based method of determining the polar of a point. And then after we've found those 2 extra points here and here, we just connect them by this blue line, and that's the polar. And I might as well tell you, just for a completion, to work out the pole of a given line, it's pretty easy. So if we just rewind, now you know how to find the polar of a point. Let's say you're given a line like this red one here, or just pick a pair of points on that line and determine the polars of those points, and the place where those 2 polars meet, that will be the pole of the line. So if we rub out the initial line and we look at the point we've just found and we find it's polar, yep, that'll be the initial line again. So this is a very rich kind of object, is a polarity, but in fact a polarity is really an even more fundamental thing than the conic in a way, because if we know the polarity, if we know how the points and the lines are swapped around, then we can determine the conic itself to be the set of all points which are sort of touching their own polars, or the set of all kind of self-conjugate points, as it's also as some people would say. So given the polarity, you can find the conic. And so thinking about a conic as a polarity, or thinking about a conic as a sort of representation of a polarity, is a more sophisticated viewpoint which takes into account the kind of complex structure of a conic. Another way to think of it is in terms of the involutions which are induced by a conic, by a polarity associated with a conic. Okay then, so like I say, a conic, like a circle, can be associated with these polarities, and it's perhaps better to think of it sort of corresponding to a polarity. Now, a lot of my thoughts on projective geometry are influenced by a book called Projective Geometry, by an author called Lawrence Edwards, and he suggests that a conic should be thought of as the set of all projectivities that it induces upon different lines. Now, there's lots of different projectivities that a conic can induce upon a given line. I've actually done quite a bit of research on this, and I don't want to go into it now. But what is more natural is, rather than thinking of all of the projectivities that a conic can induce of a line to itself, one can just focus upon the sort of period 2 projectivities, or the so-called involutions. And there's a couple of advantages to doing this. One is that we can naturally produce these involutions just by sort of taking a cross-section of what's happening with our polarities in some sense. And secondly, these involutions provide a sort of direct representation of the imaginary points of the conic, if we're talking about imaginary points, or indeed they provide a representation of the real points of a conic. Not that we need them, because real points can just be represented by dots, of course. But anyway, so thinking about the conic as the sort of set of all involutions that it induces upon the different lines in the system is quite a healthy approach. So what do I mean by an involution induced by a conic upon a line? Well, here in this picture we have a purple line, and the circle is inducing a particular polarity upon this, a particular involution upon the points of this purple line. And it's fairly easy to see how this works. Just have a sort of point upon this line, and to determine where it's mapped to under this involution, you can just draw the polar of this point, and that's going to be this blue line here. And the place where this blue line meets the purple line is going to be the place where this point is mapped to under the involution. So you can see here how this involution is working upon this purple line. Now I've also put a couple of red points here, which are just another pair of objects and images under this kind of involution. So the red solid point is mapped to the red sort of hollow point, and you can see that this is a period 2 mapping because it's sort of swapping around these 2 points. It's an involution swapping around pairs of points on this purple line. So in fact this involution is a sort of representation of the 2 complex points where this purple line meets the circle. I'll talk a bit more about that in a moment. Essentially there are, maybe it's best to say it like this. You see this involution working on this purple line, and we can ask where are its fixed points. You might say it has no fixed points, but it would be better to say it has no real fixed points. In fact, if we determine its fixed points, they are complex or imaginary points, and they constitute the points where this line meets the circle. Now, another thing just to notice here is that this involution has the property that if we look at these sort of pairs of points that are sent to each other, so the pair of blue points and the pair of red points, then they separate one another in the sense that if you take a sort of direct path from a blue point to a blue point, you have to go through a red point, and vice versa. And involutions which have pairs of mates that separate each other are so-called circling involutions. They're precisely the involutions that have no real fixed points, precisely the involutions that represent imaginary points, and precisely the involutions that are induced by conics upon lines that don't meet those conics at any real points. To look at a different case, we can move our line so that it does intersect our conic at real points. And then we see that the fixed points of this involution are real, and they're precisely the places where the conic meets with the line. And in this case we see that the pairs of mates of the involution, a so-called breathing involution, that's an involution with real fixed points like this, the pairs of mates don't separate each other. It's possible to go from one blue point to the other without passing through a red point. So we have these 2 kind of fundamentally different kinds of involutions induced upon different lines. Lines that meet the conic at real points have these kind of breathing involutions with real fixed points. And in the case where the line doesn't meet the circle, the involution induced is a circling involution which doesn't have any real fixed points. Okay, so in this case, how can we sort of really, like, it's enough actually just to say that we can represent there's going to be 2 points where this line meets this circle, and they can be represented by this involution and by associating the line with a particular direction. So, like, algebraically, if you work out, like, solve the equations of where the line meets the circle, you'll find it meets it at 2 complex points, and those are going to be complex conjugates to one another. So which of those 2 points you're referring to, that is something which you can determine by associating the line with the direction. Anyway, there is a way to geometrically construct the sort of size of the imaginary parts of the meeting with this. You can construct the kind of properties of these meeting points of this line and this circle, these complex points. So basically this involution of this line represents the meeting points of the line with the circle. And how can we understand this in a more concrete way? Well, we can do a sort of geometric construction to find a special way to represent this involution, which gives us information about these complex points. So if we drop a perpendicular from the centre of our circle to this purple line, this place where this line meets the circle, that's going to be the sort of, we could call it the centre of this circling involution on this line. You could also consider it to be the sort of real component of these 2 complex contact points that this purple line has with this circle. Now we can find what the imaginary components are if we do this construction by drawing tangents from this point to the circle, drawing parallels to our purple line where it's perpendicular that goes through the centre meets the circle, so we've just drawn those tangents and those parallels, and if we find the 4 points that those meet at, the 4 finite points, that gives us a quadrangle, and we add in the other 2 lines we get by joining points of that quadrangle, and those give us 2 new points on the purple line. Now the distance from the centre to one of these points is going to be the size of the imaginary components of the contact points of this line with a circle. You can verify that using Cartesian kind of algebra just by solving where the line meets the circle in complex numbers. But these points also have interpretations with respect to the involutions. So in particular, this centre point here, under this circling involution which the circle induces upon this purple line, this central point is swapped around with the point at infinity on this purple line, and these 2 amplitudal points are also mates with each other, and in fact they're sort of harmonic to each other with respect to the centre and the point at infinity. That's another way you can find these amplitudal black points on this purple line. So this is kind of a canonical form for involution, and what we can also do is if we draw a circle centered upon the center of the involution and passing through the amplitudal points, maybe a semicircle is easier to work with. Well, if we determine where this meets the perpendicular, then we get yet another way to work out how this involution goes. Because to work out the image of a point, say this blue one, we just draw a line from it, from this point on the semicircle, then a perpendicular to that line, and what we find is that that perpendicular goes through the image of that point under the involution. So the involution itself can be considered to be a sort of result of a 90-degree rotation about this extra point. These are just some nice properties of these kind of circling involutions, these involutions without real fixed points. And it's these kind of involutions which are induced by a circle with a real line that it has no real points in contact with. If one looks at the sort of effect of this kind of polar mapping, this polarity upon the points of a particular line. Now what we can also do is we can say, well, what about the family of all lines which are parallel to this purple one? Where do all of those meet the circle? Well, of course, if the line's close enough to the middle of the circle, it'll meet the circle at two real points. If it's far away, it'll meet it at two imaginary points. And these black points here, they give the kind of amplitudes or the size of the imaginary parts of those points. They're not the points themselves, they're just representations of the amplitudes. The points themselves will be a complex point and its conjugate, and which of those we're referring to can be determined by which direction we associate with this carrier line. This purple line, which can be thought of as a sort of carrier of the complex points. The points come in pairs, which are complex conjugates of one another, and they're always joined by a real line. There's always a common real line between a point and its complex conjugate. Anyway, if we turn on the trace of these sort of amplitudal representation points, then we can shift around our line and we see the sort of representation of the complex part of a circle. It's a rectangular hyperbola that tells us the sort of amplitudes or size of the imaginary contact points that this line has in common with the circle for different lines of different distances away from a circle. Now this is just for one family of parallel lines, and this kind of picture, if you want to consider a family of lines in another direction, then you can just see what kind of rotation you need to do with your line to get the new direction, and then just rotate this picture of a rectangular hyperbola by that direction. And so by this we see that the circle has a kind of it has a sort of one-dimensional continuum of real points, but also just for this family of parallel lines there's a one-dimensional continuum of imaginary points, but then there's another one-dimensional manifold for every other direction. So in a way the circle kind of is like a sort of two-dimensional manifold, not just a one-dimensional curve. So this is for an ordinary circle with a real radius, and what we can see is happening is that as this line gets close to the circle, these imaginary points kind of coalesce together, and then at this place here there's just one kind of real point, and then these real points separate out to be two real points as we consider lines that are close to the middle of the circle. And we get a kind of similar picture for the case with a circle with an imaginary radius. It's just that in that case we never have this kind of coalescing of our imaginary points to become real. They stay as distinct imaginary points all the way along. And we still have a hyperbola swept out, but it's the kind of hyperbola that opens up in the other way so that it doesn't collapse down in this respect. You'll see the picture in a few moments. Okay, so then before I did a construction of an ordinary circle using perpendicular lines, and if you recall I used two light blue points and then I drew and those were considered to be diametrically opposite each other on the real circle, and I drew a line through one of the points and a perpendicular line through the other one, and those two met at a point on the circle. So then varying the first line drawn and keeping the other perpendicular to it, the two lines meet at variable points upon the circle. So that's a construction for the real circle, and now we can basically do the same kind of construction but for the imaginary circle. And for our sort of diametrically opposite points, we shall call them A and B, and since all of the points on the imaginary circle, the circle with imaginary radius, since all of its points are imaginary, we have to start with a pair of imaginary points, and we shall pick complex conjugates imaginary points. We'll call them A and B, and so those two are both associated with this kind of circling involution upon this line, the circling involution that swaps around these points N and M, and it also swaps around this central point with the point at infinity on this purple line. So this is how we start, and then what we're going to do is to draw a sort of arbitrary line out of this joining one of these complex points out of such a point. We're just going to draw an arbitrary line. We're going to draw a complex line. So the way we can do that is just to pick a sort of extra point upon the plane, a real point, and we'll suppose that that real point, we'll call it X, and we'll suppose that that point is the sort of carrier of a complex or imaginary line which is joined to point A here. So the way this looks in practice is that we pick this point X, I'll pick it here, and then we just join that to these pair of amplitudal points M and N, and so they're going to be mates of this involution of lines through X, and also the central point is going to be a mate to the line through the central point is going to be a mate of the line perpendicular to it, and so we can see that there's a sort of involution induced upon the lines through this point X, and since this involution's in perspective with the involution of points upon the line, this involution of lines through X is a sort of representation of complex lines which are joining X to a complex line which is joining X to A. Now, just like the way that the involution upon the line through A and B can represent either A or B, and it's only by specifying a direction to the line that we can differentiate between the two complex conjugate points, so this involution of lines through X could either represent the line joining X to A or the line joining X to B, and it's only by associating this involution of lines through point X with a sort of rotational direction that we're able to differentiate between the two scenarios. So for that reason we associate this involution of lines through X with a specific direction. So in this case if it's let me get this right, if it's an anti-clockwise rotation, then that corresponds to the point J, which joins, sorry, the line J, complex line J, which joins X and A. If it's a clockwise rotation, that represents the line K, which joins X and B. So there's two kind of complex conjugate lines here represented, which have a real carrier of X. Now, what we're going to do is rotate this. Well, let's just consider the complex line J, which joins X and A and is associated with the anti-clockwise rotation about X. And we're going to rotate that complex line by 90 degrees. So the way this works in practice is just to look at all of the, well, here we have two pairs of mates under the involution of lines through X. And we just look at the kind of 90-degree rotation of all of those lines. And so that'll give us a sort of complex line which is like this line but rotated by 90 degrees. It's perpendicular. And we want to consider such a perpendicular line that's going through point B. So in practice, what that means is that the sort of representations of the amplitudes of that line ought to go through N and M. And so the line perpendicular to J, which we'll call J dash, and it sort of looks like this represented by the green and black lines. And so essentially it's another involution, and it's swapping around the two green lines and swapping around the black solid and the black dotted line. And to make sure that this and then this 90-degree rotated line ought to, we can call it J dash, and it ought to pass through point B. So then J dash is associated with again an anti-clockwise rotation of the lines through this point X dash. And so we have these two complex lines that are perpendicular to each other. The line J joining X to A and the line J dash joining X dash to B. And what we want to do to find a point upon our imaginary circle is to just find where those two perpendicular lines meet each other. And they're going to meet at the sort of well, they're going to meet at a complex point, and that complex point is going to be represented by an involution, which is going to be sort of in perspective to both the involution of the lines through X and the involution of the lines through X dash. So it's quite easy to find such an involution. We just see where these green and orange lines meet at the new line. And so they meet at points S and T. And so if we draw a line through that, a dark purple line, that's going to be the carrier of the kind of complex meeting points of the orange and the green lines. So another way to say it is that the involution of the orange lines and the involution of the green lines are both in perspective to this involution on this dark purple line. And so that means that what's going on this dark purple line is representing complex points. The involution on it is representing, well, a complex point upon the circle, the meeting point of J and J dash. And that's associated with the rightwards direction, and we'll call it point P. Now we can do just the same thinking, but instead we can start with point B, and we can join B to X and then rotate it 90 degrees and draw a line through A. Now diagrammatically we have nothing to add, but basically what that corresponds to is instead we're considering the complex line K through X, which corresponds to a clockwise rotation and links X to B. And then rotating K by 90 degrees we get the line K dash, corresponding with associating with this involution of lines through X dash with a clockwise rotation. And that's going to be a complex line joining X dash to A. And that gives us the sort of extra direction, well, that gives us the opposite direction associated with this dark purple line. It essentially gives us another point upon the circle, the complex conjugate of P. So now we have 2 points, P and P dash, 2 complex points on our imaginary circle. Now this is just for one specific complex line. Well, we'll just think of the one drawn out of A, and then we rotate it by 90 degrees and draw it back in through B, and we find out where those 2 complex lines meet, and those meet at the complex point P upon the circle. But to find out all the points, all the imaginary points upon the circle, we don't just want to look at one complex line, we want to look at all of them. So we have to kind of vary this line to sweep out points upon the circle. So what we can do is, if we just move X upon this construction, then we're essentially considering different kinds of imaginary lines that we're drawing out from A. And by getting such a line, rotating it and drawing a perpendicular back in through B, finding out where it meets the initial line, we get all sorts of different points upon the imaginary circle. And in fact what we're doing here, by sweeping out this diagram, I mean, here I've picked a special case where X is the carrier of the line J. This point X is a sort of variable point upon the perpendicular to the centre of N and M. And if one does this, essentially one finds all of the places where this imaginary circle meets these different lines which are parallel to our initial purple line. And you see that a hyperbola is swept out. Now you can contrast this with the hyperbola that we found before, showing the meeting points of a real circle with an imaginary line, in the sense that that hyperbola, it was again our rectangular hyperbola, giving us our amplitudes, but that one collapsed down to a point and then sort of vanished and became real, and we got a real circle that looks like an ordinary circle. But here our kind of hyperbola, which represents the amplitudes of the complex meeting points of our imaginary circle with the different dark purple lines that we can draw in this family of parallel lines, well, this hyperbola never collapses down. And that's another way of saying that our imaginary circle never meets any line of this parallel family at real points. And in fact, there's nothing special about this direction. Exactly the same kind of picture is determined if one picks any other direction. So basically, to draw out the whole imaginary circle, we can just take this kind of picture that we can get by varying things along this line, and then one could just consider a sort of rotation of this picture if one's interested in where this imaginary circle meets with a different family of parallel lines. also, what's the centre of this imaginary circle? Well, the centre of an ordinary circle is the point that's polar, is the line at infinity. So if one draws a diametric line through the middle of an ordinary circle, and one says, okay, I want to find the centre, which point upon this line is the centre, well, what one can do is determine the kind of involutory partner, the kind of mate of the different points under the involution, and the point that's mated with the point at infinity upon that line, in other words, the point whose polar is the line at infinity, well, that will cut this diametric point at a point at infinity, and that must be the centre of the circle. And just the same thing is true for the imaginary circle. So as I said at the beginning, this real line, this light purple one through A and B, if we want to find the sort of centre, well, we can find out the sort of mate of these different points under this involution, and it's precisely the involution which represents the imaginary points we're starting with. So as I said before, a way we can think about this quite easily is just in terms of a 90-degree rotation about the sort of top of this semicircle. And so this 90-degree rotation is the way this involution works. And you see that N and M are in involution with each other. They're going to be mates with each other. And as I've already said, this central point, the midpoint of M and N, is the point which is swapped around with the point at infinity. So since this light purple, or maybe pink, magenta I suppose, this magenta line here is the diameter of our imaginary circle, or a diameter of our imaginary circle, we know that this central point between N and M is actually the centre of our imaginary circle. So an imaginary circle, a circle with an imaginary radius like this, does indeed have a real point. Does indeed have a real central point about which it's drawn, just like an ordinary circle does. It's just that all of the points on the circle are imaginary, but the middle of it is a real point. The centre of it is a real point. Okay, so I think it's fairly difficult to understand that last construction if one hasn't seen it before. It takes a bit of work, and so I think it's probably worth watching what I've just discussed before again, and making sure that you understand the construction steps properly a couple of times. And also you may want to watch my video, The Projective Nature of Circles and Imaginary Lines, because in that video I talk about the idea of what imaginary lines are and how you can join together imaginary points by imaginary lines and so on, and then it will start to make some more sense. Another way we can get more of a grip on what's going on is to do that same construction, but we're going to do the kind of real analogue of it. So we're going to take another look at how to make a real circle. So we start with a couple of real points A and B on a sort of diameter that goes through the centre G of the circle. Now if we'll pick an extra point X, and it can be any point actually, but we'll have it lying on the sort of bisector of the midpoint of A and B. So X lies upon this line that's like perpendicular to the centre of G of our circle, and as we vary X, that varies the nature of this line K, which is joining A and X. Perhaps I should have called it J, to have consistent notation with the last one. But anyway, I'm calling it K here. I think maybe I've got K and J the other way around here. But anyway, hopefully it won't alter much of your understanding of it. So we have this red line, and then all we want to do to find a point on our circle is to draw something perpendicular to this red line through B. So that will be easy enough, and then we can just vary X to get different red lines, and the place where that red line and its perpendicular meet will be a point on the circle, and all the points on the circle will get swept out this way. That's fairly simple. But we want to consider this in terms of involutions. So just like last time, I mean, in the last construction we were working with imaginary points, so we didn't have the luxury to take such a simplistic view. We had to use involutions to represent our points. So we can do the same thing here. It's just that here, when we have real points, we represent those by breathing involutions, which have fixed points as the points that they're supposed to represent. So that's no problem. We'll just think about an involution of this diameter line, this black horizontal line, and the involution we're thinking about has fixed points A and B, and it also switches around this point G with the point at infinity, and it switches around these points N and M. So these points N and M are a pair of mates under the involution, just like they were in the last picture. The difference here is that the involution is a breathing involution with real fixed points, because the circle meets the line at real fixed points. And this involution is just the involution that the circle induces upon the line, although that's kind of putting the cart before the horse, because we're really thinking about starting with this and constructing the circle. But it doesn't really matter, because we're not so interested in actually constructing the circle here. We want to follow through the logic and see how it's analogous to the previous construction. So what we can do, rather than just taking this kind of simplistic view of draw line, draw perpendicular, got a point on the circle, we'll join X to all of the points on our to 4 of the points on our breathing involution. So we'll join it to these fixed points A and B, and also to these pair of mates M and N. And this gives us a couple of fixed lines, these solid lines, and a couple of mates, these dotted lines, under the sort of corresponding breathing involution of the lines through X. And so we'll call these dotted lines N and M, and they're going to be switched round by this involution of lines through X. So what we're going to do now is find a sort of rotation of this setup and find a perpendicular sort of setup. So we're just going to rotate this thick solid line through A, this point that's joining A and X, by 90 degrees, and find out where that goes through B. And if we do that, we find that it meets this line perpendicular to G at this point X dash. So X dash is like the sort of carrier of these lines we get by rotating the red lines through X by 90 degrees. And so by rotating each of those lines, K, M and N, we get the lines K dash, N dash and M dash through this point X dash. Now it's easy enough to see that rotating the point K rotating the line little k through X gives us this line little k dash through B, and that's going to be a fixed line of the involution through X dash, and it's going to meet with K and K dash are going to meet upon a point of the circle. But what else is interesting is if we look at where the other kind of corresponding red lines and blue lines meet, they're going to meet at points which are, they're going to meet at sort of corresponding points, and essentially what we see is that if we join the two fixed points Well, what we see essentially is that we get this kind of purple line upon which the same kind of breathing involution exists, which is in perspective with the involution of the lines through x and the involution of the lines through x dash. So, in other words, there's a sort of involution induced on this purple line, which is in perspective with the involution of the lines through x and the involution of the lines through x dash. And so then the fixed points of where that purple line meets the circle, joining those fixed points to x gives the fixed lines of the involution of lines through x. Joining those fixed points through x dash gives the fixed points of the involution of the blue line through x dash. And what are these fixed points on the purple line? They're just the contact points of the purple line with the circle. And we can call those points P and P dash. So they're going to be real points in this case. But we can see now what the kind of we can see the kind of connections here between this and the setup we were just looking at, which was maybe more complicated for the case of the imaginary circle. Okay then, so let's talk about the sort of polarities which are induced upon the points and lines of the plane by these objects. So firstly we'll have a look at the circle with a real radius. So we can just use this GeoGebra command to find the polar of this purple point, make this line purple, and we can see the relationship here. Now there's an interesting fact about the polar of a generic point on the plane in this case, and that is that if we join that point to the centre of the circle, then the polar of that point is going to be perpendicular to that joining line. So that's some useful information, and we can get even more understanding if we note that the position where this purple line intersects this perpendicular line, we can mark that maybe a pink point. So the position of this pink point with respect to the purple point is going to be the harmonic conjugate of the purple point with respect to the two meeting points this black line has with a circle. In other words, this circle is going to induce a certain type of involution on this black line. Now, since this is a circle, in this involution, the point in the centre of the circle is going to get mapped to this sort of line at infinity, so that mate of the central point on this line is going to be the point at infinity on this line. And the two fixed points are going to be the points where this line meets the circle. So this gives us a sort of method to work out what the mate of a given point is for this case on the real circle, sort of automatically. So the way we can do it is well, if we just draw a couple of lines out, so we're going to do a quadrangular construction. This is a standard way to find the harmonic conjugate of a point. So we take one of these fixed points, we draw a couple of lines out of it, and we draw a line out of the thing we want to find the harmonic conjugate of. This makes us a couple of points. Whoops. And then we draw a couple of points out of it, a couple of lines out of the other fixed point. and then we basically get the other 2 points of the quadrangle we're looking for. So now we have these 4 points, 3 pink and 1 blue, of a quadrangle, and we find that the other opposite edge of the quadrangle indeed goes through this pink point. So we could have used all this information without knowing where this thing is, and then we find where to position this pink point, and we just draw a perpendicular line. Whoops. And that's the method to find the polar of a generic point with respect to a circle. And for this ordinary circle, of course, we're dealing with real points here, and we find that the kind of points touching their own polars are going to be the points, the real points of the circle. Those sort of corresponding dually to the tangent lines to the circle. So basically we can consider a completely analogous construction to determine the polar of a generic point with respect to an imaginary circle. So let's do that now. So our imaginary circle, we can define it like we did before by a line, to basically say there's an involution on this line, and it's this line is a diameter of our imaginary circle. Okay, so as we were investigating before with our rectangular hyperbola drawing, we can find this sort of center point between, let's say these 2 points are giving the amplitudes of our involution on this line that's a diameter. So then so these 2 points, these blue points, are swapped round by this involution. It's going to be a circling involution, and this grey point here is going to get swapped round with the point at infinity. So this is a sort of imaginary version of the circumference of our circle. I'll just draw the actual circle out just for clarity here. I'll just do it quickly. I'll draw the imaginary part of this circle for lines parallel to our initial black line. So it's fairly straightforward. We just draw a couple of lines through here. So this is representing an imaginary line. Then we find a perpendicular to it. This gives us another imaginary line with a carry down here. We vary this, and then these 2 imaginary lines are going to meet at this imaginary point with amplitudes down here. And then we can put the traces of these things on. And there we go. This is showing us the amplitudes of the imaginary points where this imaginary circle meets this family of real lines parallel to this, well, horizontal black lines. Anyway, rewind all that. That's basically what our initial setup means. But the same kind of setup's going to hold for anything, for any other family of lines, a different direction. It's just the setup's going to be correspondingly rotated. So I think it's a nice idea to visualize this imaginary circle just by a dotted circle, since it has the same kind of circular symmetry and such. So now, let's say we have a generic purple point, and we want to find out its polar with respect to this imaginary circle. So how can we do it? Well, just like before, the polar of this point is going to be perpendicular to the line we get by joining this point to the centre of our circle, our imaginary circle in this case. So we know that. We also know that there's going to be an involution upon this circle, and it's going to be the same kind of involution as the last one, just rotated. So we can put these 2 points here, and these are going to be the amplitudes of our involution. So basically, what we know now, I'll make this line green just to make it easier to talk about. So what we know now is that on this green line, these two blue points are getting swapped around by an involution, and this grey point is getting swapped around with a point at infinity. And what we want to do now is to find the mates of the purple point with respect to this involution. And once we've done that, basically we just draw a perpendicular to that point, and that's going to be the polar line of our purple point. So we can do that in various different ways, but there's a sort of special trick with this being a circling involution involving finding a sort of centre of rotation. So it turns out if we just draw a perpendicular and see where, find the point on that perpendicular as high above the centre as the blue points are away from the centre, well, that's going to be a sort of centre of rotation. And then what we can do is join this point here by a line, make it a dotted line, and then find a perpendicular to that, and that's going to give us our mates. I'll make it pink to match up with the last one. So now all we do is just draw a perpendicular through that point, and that's going to be the polar of our generic points. So there we have it, a visualization of a sort of polarity induced by an imaginary circle. And we see here that there are no points now that are going to be touching their own polars. And this whole kind of setup has a very interesting interpretation in 3 dimensions, in fact. So I don't know if I can quickly look at this, if I can just add on the 3D aspects. Is it going to let me? Okay, that's cool. So what I can do okay, so I've got my circle in the plane, and let's just recall what's going on here. Okay, so I think what I should do now, I'll go to the 3D construction, and I'm going to draw a perpendicular line out of the centre of this. There we go. And now if I draw a sphere, so I want to find a point on this perpendicular that's just as high as the radius of this sphere. Let's hide the sphere again. So now this new point I've got, which is like, if the circle is if this is an imaginary unit circle, unit radius, well, radius of I essentially, if it's got a radius like that, then I can put this point a unit above the plane, a real unit above, and then there's a pretty nifty way to find the polar of a generic point. So okay, let's make this perpendicular line. Make it dark purple for perpendicular, and then we'll draw a line. Whoa, what's going on now? We'll draw a line going down through this purple point, say a red line. I said red. And now what we're going to do is make a perpendicular plane through this point I've put that's going to be perpendicular to this line, and lo and behold, see that perpendicular plane I've just drawn is exactly cutting the initial plane at the polar. So we get a new interpretation. This is something I found out for myself. I must say I haven't rigorously proved it, but I think it's fairly easy to prove just by looking at the thing based on rotation. But we find this sort of new interpretation of the polar of a point on the plane with respect to the imaginary circle, and it's really very simple. It's just, okay, you've got a circle with a given imaginary radius r, so find its centre, which is a real point, and then out of the plane stick another point, a distance matching the imaginary radius above that point in the plane, in a perpendicular direction to the plane, and then that point is sort of the pivotal point that describes the polarity, in the sense that to find the polar of any point in the plane, just connect it by a line to this pivotal point, and then find a plane perpendicular to that pivotal point, and that plane perpendicular is going to cut the line at cut the plane at a line which is going to be the polar of the point that we want to find. That is going to be the polar of the point that we put down, the object we're interested in. So basically, polarities under imaginary circles just correspond to that kind of this perpendicular relationship between lines and planes. And for this reason, I think the imaginary circle is a pretty fundamental object. Okay, so it would be nice to be able to do geometric manipulations with a circle of imaginary radius, just like we do with an ordinary circle. So to do that, we ought to be able to do a couple of elementary constructions, in particular finding out where an imaginary circle meets a given line, and finding out where two imaginary circles meet. So there's a way of doing this fairly simply, by making some kind of tools in GeoGebra, just to make the construction faster. So, as I've discussed before, an imaginary circle can really be defined by specifying a sort of line that goes through its centre, a diameter if you like, and then by specifying the kind of circling involution it induces upon that diameter. So a simple way to do it is just to put a couple of points down that represent the amplitudes associated with that involution. And that's sort of a canonical form of such a circling involution, the two amplitudes, and the midpoint of the amplitudes being the point that gets swapped around with the point at infinity under the involution. That's the centre of the imaginary circle. So given all this information, one basically can define the thing, and then what we can do is, suppose we're interested in a given line, say this one here or whatever, and we want to know where this meets the circle. Well, there's a fairly straightforward way of doing that. Might as well make this line orange just to distinguish it a bit. So then the construction would just be find a perpendicular to that and a parallel through the centre, make a couple of analogues of these dark blue points, and then we can just construct this kind of rectangular hyperbola which describes the kind of amplitudes at which this imaginary circle will meet lines parallel to our orange one. So we draw a generic imaginary line out of these points, then a perpendicular to it, and then the imaginary point at which those two imaginary lines meet. And there we have it. That's going to be a couple of points on our imaginary hyperbola. Now we know that our imaginary hyperbola also goes through these diametrically opposite points, these black ones. So let's just do this construction again, but we want to do it sort of, actually, I'll go back. Let's try and be a bit cleverer about this. So we can pick this point here, because we want to do all of this without adding any extra variables. So if we find a midpoint here and another midpoint, we'll make two constructions based on these. So that's one, and the perpendiculars, and that gives us these amplitudes here. And then we'll do it again. So for this one we get these lines here, okay, I'm starting to get a bit confused. Right, so we're talking about these lines. So what's the perpendicular to this one? There it is. Okay. Right, well, to avoid confusion, let's make these points red. And we can rub out this. Okay, so now we're going to use a new point. We'll draw these lines like this. And they're perpendiculars. This is looking better. And this gives us a couple of new points on our rectangular hyperbola. Okay, great. So we have now 6 points on our rectangular hyperbola. You only need 5 to define a conic, so 1, 2, 3, 4, 5, and there we have it. This hyperbola here, this is giving us the amplitudes where different lines parallel to this orange one meet our circle. So let's make a tool now to construct this automatically. So create new tool. The output should be this hyperbola, and the inputs will that do? Yeah, okay. So tool name, image circ. finish. Okay, so this is basically automatically determining where our imaginary circle meets a given line. So if we just, let's quickly erase all the constructions we've got so far. Well, hide them at least. Now, to define a given imaginary circle, we just put a couple of points down anywhere we like. Suppose that's an amplitude. So if we want to actually draw our representation of a thing, we can do it like this. Our dotted circle. And now, using our tool, if we have another sort of generic line, we can just click on our tool and go point, point, line, and we have the sort of rectangular hyperbola which meets our line. That ought to be variable, shouldn't it? No, it varies on direction, of course. So this rectangular hyperbola meets our line at the points giving the sort of amplitude. So if we want to, for example, work out the involution that's induced upon this line, we can just find out where it meets this rectangular hyperbola and draw a semicircle. And a perpendicular, and then this is going to be the centre of which gives our kind of involution. So if we have a generic point here, just connect it to our rotation centre and find the perpendicular of it. And this is the involution induced, and you see it swaps around these two amplitudal points and swaps around this point at infinity. So basically this is pretty nice because it gives us a way to sort of visualise this imaginary circle in general. And this basically allows us to find out where the imaginary circle meets a given line. Okay, so where do two imaginary circles meet? Well, that's fairly straightforward. If one notices that, well, essentially this construction lets us know where the circle meets a given imaginary line, and it's doing so by drawing this rectangular hyperbola, and the sort of central line of this rectangular hyperbola, the sort of line that goes through the middle of where it folds out from. It's difficult to, I don't know what the proper terminology is, but I mean sort of, in this case, the line I'm colouring green for this particular rectangular hyperbola. So we know that this sort of rectangular hyperbola is showing the complex points where this imaginary circle is meeting the line perpendicular to this sort of central line. So we can use this fact. So let's just do some rubbing out now. So suppose we have a couple of imaginary circles. So we can draw another one over here. So how do we find out where these two imaginary circles meet? Well, we just draw a line between them, and then we want to work out where these two imaginary circles meet, and they're going to meet on a line perpendicular to the line joining their centres. So this is a theorem which holds for ordinary circles as well. that their common chord is going to be perpendicular to the line connecting their centres. So all we do now is just sort of, well, let's just pick any old line that's perpendicular to this centre joining line, say here, excuse me, whoa, that's weird, let's try again, make sure it's, there we go, and then we'll just use our tool to find out where these circles meet this line. So the left circle, might as well colour it purple. The purple circle meets this line at the purple hyperbola, and the green circle is going to meet this line at this green hyperbola. So joining these two, we find that at this particular line, which I shall colour orange, this is the kind of common chord between these two imaginary circles. And because these two circles, they give the complex points with the same amplitudes on this real carrier line. So this is where these imaginary circles meet. In fact, any two conics will meet at 4 points. So these two complex points represented here, it's actually 1 point and its complex conjugate, are represented here on this orange line, and they're finite meeting points. But these circles will also meet at those two imaginary points at infinity. Every pair of circles have those points in common as well.